Namaste, myself, Sachchida Nand, Assistant Professor, Department of Mechanical Engineering, with the Institute of Technology. So, today we are going to start with the impact testing. As in the earlier lecture, we have discussed about the destructive testing and non-destructive testing. That means what is the meaning of destructive means and what is the purpose of non-destructive means. So in the mechanical engineering, it is very much required that to check the physical property, or as you can say, the mechanical property of a material. That material which is gone through the various processes and are projected at its working environment. So what are the needs to study that particular impact test? Why it is required? So before proceeding for the impact testing, we need to understand what is toughness. Because the toughness is the property of a material which absorbs energy and then fracture. As you can say, it absorbs energy till its fracture. So the toughness, since the impact test is the only one method by which the property, this material's property is based. So what is toughness? That how tough that material is to resist the sudden load, impact load. So that toughness is broadly a measure of the amount of energy required to cause an item, a test piece or a bridge or a pressure vessel to fracture and fail. The more energy that is required, then tougher that material. So why we are introducing this word tougher? That particular material should have the property that it can withstand in the critical scenario during their working condition or working environment. That if a material or a product which is made by the material are working in an open environment and suddenly something is hit directly onto that particular product. So what will be the condition? And what will be the scenario of that particular material which will be impacted or which is impacted by some other material? दोनों ही मटेरियल्स के ऊपर कुछ न कुछ एक्शन और रिएक्शन फोर्सेस अप्लाई होंगे. तो जो भी प्रोडक्ट या कोई भी ऐसी चीज आके किसी प्रोडक्ट पे टकराती है तो उस पर्टिकुलर मटेरियल पे उस टकराने के रिएक्शन को कितने हद तक वो सह सकता है बिना अपनी ओरिजिनलिटी, अपने स्ट्रेंथ को डगमगाए हुए, तोड़े हुए. या फिर आप ऐसे कह सकते हैं कि टफनेस ऐसी प्रॉपर्टी है मटेरियल की जो सडन लोड को, सडन झटका को सह सके बिना टूटे हुए। और इस इंपैक्ट टेस्ट की सबसे बड़ी एग्जांपल टाइटैनिक शिप है, जो अपने पहले जर्नी में ही डूब गया था। और जब उस डूबने के बाद उसके जहां पे वो डूबा था वहां से उसके मलबे को निकाला गया और उसके बाद बहुत सारे इंजीनियरिंग टेस्ट उस पर्टिकुलर मटेरियल्स के ऊपर या बहुत सारे एनालिसिस की गई कि यह मटेरियल डूब कैसे गया, जबकि इतनी टेस्टिंग करके इसको हमने एक फाइनल प्रोडक्ट बनाया हुआ था। सॉरी, सो हाउ इट दैट हैपन, हाउ an iceberg will impact on the toughness of a metal which is tested several times on various parameters to withstand in that southern ocean. But something was not tested according to the situation, according to the working situation of that particular Titanic ship. So what was that? So after examination, after analysis of that particular ship, the engineer found that the material have a tendency, that they have the tendency to change their structure from ductile to brittle. And how is that happen? How is that possible? It is just because possible because of the change in the temperature. So as you can say, the change in the working temperature of the particular material. So टाइटैनिक के साथ हुआ क्या? जब उस टाइटैनिक को बनाया गया तो वो नॉर्मल रूम टेम्परेचर पे या कुछ हद तक के रूम टेम्परेचर पे उसको टेस्ट किया गया, लेकिन जब वो पानी में उतरा और जब वो चल रहा था तो उसके वर्किंग इन्वायरमेंट के टेम्परेचर में चेंजेस आ गए। क्या चेंजेस आए? जब वो मटेरियल बनाया गया धरती पे बिना उसको पानी में उतारे, तो उस समय की जो टेस्टिंग रही वो अलग टेम्परेचर के बिहाफ पे टेस्ट की गई, और जब वो अपने वर्किंग इन्वायरमेंट में उतरा तो वहां पे -10 डिग्री सेंटीग्रेड पानी का टेम्परेचर था, जिसके वजह से उस मटेरियल की जो टेंडेंसी थी डक्टाइल नेचर की, वो धीरे धीरे ब्रिटल नेचर में तब्दील हो गई। और ये सिर्फ हो पाया टेम्परेचर डिफरेंस की वजह से। और जैसे ही वो ब्रिटल मटेरियल में तब्दील हो चुका था, बस उसे एक झटके की जरूरत थी, एक इम्पैक्ट की जरूरत थी, क्योंकि आपको पता ही है ब्रिटल मटेरियल कितना आसानी से टूट जाता है लाइक दिस। क्यों? क्योंकि इनकी बॉन्डिंग जो है वो उस तरह से नहीं होती जिस तरह से हमें डक्टाइल मटेरियल में मिलती है। और यही कारण है कि जब स्ट्रेस स्ट्रेन कर्व पे हम ब्रिटल मटेरियल के स्ट्रेंथ टेंसाइल स्ट्रेंथ को चेक करने जाते हैं या प्लास्टिक डिफॉर्मेशन को चेक करने जाते हैं, तो वो प्लास्टिक डिफॉर्मेशन से जाने से जस्ट एक पॉइंट पहले जो प्रोपोर्शनल लिमिट बोला जाता है, जिसे जहां पे हुक्स लॉ भी अप्लाई होता है, स्ट्रेस इज डायरेक्टली प्रोपोर्शनल टू स्ट्रेन, वहीं पे वो खत्म हो जाता है। It means it break down at that point due to the brittle in nature. Why? Because the structure of that particular, the microstructure of that particular material is possessing a very hard structure that is called martensite. And that martensite hard in nature but brittle in nature also. And due to that structure, the brittle structure in that particular scenario of the Titanic. तो हुआ क्या, ठंडा पानी था, मेटल तो अपने नॉर्मल टेम्परेचर से था, ठंडा हुआ, फ्रीज होना शुरू हो गया, जो डक्टाइल नेचर था वो ब्रिटल नेचर में तब्दील होना शुरू हो गया, एक तरह से उसकी गोली क्वेंचिंग होनी शुरू हो गई, और उस क्वेंचिंग के वजह से जो उसका डक्टाइल स्ट्रक्चर था वो बदल के ब्रिटल स्ट्रक्चर में चेंज हो गया, और जैसे ही वो आइसबर्ग से टकराया, आपको पता ही है कि ब्रिटल मटेरियल कितना ही इलॉन्गेशन प्रोसेस नहीं करता है, और टकराते ही वो उसके अंदर ब्रेक हो गया। बस तब क्या था, एक ब्रेक की जरूरत थी, एक क्रैक की जरूरत थी, जैसा कि हमने पहले भी क्लास में डिस्कस किया हुआ है कि एक छोटा सा हेयर क्रैक ही काफी होता है उस पर्टिकुलर पॉइंट पे उस पर्टिकुलर स्ट्रेंथ को आइडेंटिफाई करने के लिए, और वहां पे स्ट्रेसेस बढ़नी शुरू हो गई, पानी का दबाव बढ़ना शुरू हो गया, और धीरे धीरे देखते देखते पूरा जो टाइटैनिक जहाज था वो पानी के अंदर समा गया। सो वहां से जो इंजीनियरिंग की एक नई मिसाल निकल के बाहर आई, उसको टेस्ट करने के बाद वहां से एक नई टेंडेंसी के बारे में पता चला मेटल के, कि अगर टेम्परेचर चेंज होता है तो मेटल का भी बिहेवियर चेंज होगा, और उसी को ध्यान में रखते हुए इम्पैक्ट टेस्ट को परफॉर्म किया जाता है। तो इम्पैक्ट टेस्ट ऐसा टेस्ट है, डिस्ट्रक्टिव टेस्ट, जिसमें टेम्परेचर को भी कंसीडर किया जाता है। So the area beneath a stress strain curve produced from a tensile test is a measure of the toughness of the test piece under slow loading conditions. However, in the context of an impact test, we are looking at notch toughness, that particular crack. A measure of the metal's resistance to brittle or fast fracture in the presence of flaws or the notch and the fast loading conditions. So, because of that notch, that cut, the stress concentration of that particular component or the material is increasing vastly, and due to that, the cracking propagation of in the material is taking place at a very high speed, and that's why that is the V notch and the U notch is provided in that particular impact test specimen. So, how many types of that particular things? So there are the two forms of the impact test, that is the IJOD and the CHARPY, and then another one is the also related to the impact test, that is called also known as the drop weight test. And these tests are used to determine the impact resistance or toughness of the material by calculating the amount of energy absorbed during the fracture. टूटने से पहले मटेरियल का कितना एनर्जी वो अपने अंदर अब्जॉर्ब कर सकता है, कितना टफ अपने आप को उस मटेरियल के रिस्पेक्ट में दिखा सकता है, बता सकता है, उस पर्टिकुलर प्रॉपर्टी को एग्जामिन करने के लिए मेटल के अंदर हम इस इम्पैक्ट टेस्ट को परफॉर्म करते हैं. सो इम्पैक्ट टेस्ट इज परफॉर्म एट अ वेरियस टेम्परेचर टू अनकवर एनी इफेक्ट ऑन इम्पैक्ट एनर्जी. So both involved in this particular IJOD and the CHARPY impact test. It involved the striking a standard specimen with a controlled weight of pendulum traveling at a set speed. अभी आगे फिगर में आप देखेंगे जो इंस्ट्रूमेंट है IJOD इम्पैक्ट टेस्ट का वो किस तरह से काम करता है. एक हाइट से एक लोहे के पेंडुलम को छोड़ा जाता है, तो वो विद द हेल्प ऑफ द ग्रेविटी फोर्स इतना तेजी से आता है जो उस पर्टिकुलर नोच पे इम्पैक्ट करता है सडनली, और वो मटेरियल को ब्रेक करता है. एंड दैट इज हाउ वी परफॉर्म दिस पर्टिकुलर टेस्ट, एज इट इज लाइक दैट. दिस इज द हैमर, this is the hammer which is left from a position, and then it move and it strike to that particular workpiece and left up. So we will discuss what is all about this is all about. So these tests show the metal can be classified as being either brittle or the ductile material. That will show the behavior, that is how the particular material is changed their tendency, or is showing the characteristic that how the material will behave when the impact load will apply. So brittle metal will absorb a small amount of energy When impact tested, a tough ductile metal a large amount of energy. So that is the point that defining that how the we categorize the particular ductile and the brittle material. So obviously brittle material will absorb a small amount of energy because it does not possess that particular kind of a ductility, and the ductility have a tendency to enlarge themselves, and that is how it will absorb the large amount of energy in it. So that is how this particular brittle and ductile tendency is to be checked by this particular impact test. So now further regarding this particular impact test and how this particular test is to be performed and by which standard these all are followed, and there are the various aspects which needs to be considered regarding performance of this particular test. It should be emphasized that these tests are qualitative and the result can only be compared with each other or with a requirement in a specification. They cannot be used to calculate the fracture toughness of a weld or parent metal, such as would be needed to perform a fitness of service assessment. So these tests can be performed by the specification, and that is to be done by the ASTM standard and by the ISO standard. So from the British standard for CHARPY test, that is the BS, E and ISO 148-1 2009, and the American standard is ASTM E23 is applicable to identify the particular impact test, or you can say the one of them is CHARPY. So in this scenario, the CHARPY test is the most widely used test because the CHARPY test is different from the ISO test because of the specimen position as well as the test result also. So in this scenario, in most of the time, this particular CHARPY test is widely used for examining the toughness of the material, and the ISO is now totally maybe you can say that that it may be replaceable, but you can say the CHARPY test is the most widely used test for the impact test, as well as ISO is also implemented to check the particular impact toughness of the material. So the standard differ only in detail of the striker used. So बाकी चीजों में कोई चेंजेस नहीं होते, जो चेंजेस होते हैं वो स्ट्राइकर चेंज होने में होते हैं, राइट? So the standard which RPB is specified that V is defining the notch, that particular notch from where the total stress will concentrate, and that the thing we need to identify. कि अगर कहीं किसी मटेरियल के ऊपर कोई क्रैक है, कोई क्रैक अगर बना हुआ है या बनने वाला है और उस मटेरियल पे लोडिंग लग रही है, तो उस लोडिंग का प्रोग्रेशन किस मोड में होगा, किस तरह वो उसको कम से कम सह पाएगा या बचा पाएगा, और भी बहुत सारे फैक्टर्स हैं जिनको कंसीडर करके इस पर्टिकुलर नोच को बनाया जाए। तो नोच को बनाने का रीज़न ही यही है कि मैक्सिमम टू मैक्सिमम स्ट्रेस को वहाँ पे कॉन्सेंट्रेट हो सके और जो प्रोग्रेशन ऑफ फेलियर है मटेरियल का वो वहीं पे आइडेंटिफाई हो सके, जिससे कि हमें पता लगे कि अगर इस पर्टिकुलर मटेरियल में कहीं क्रैक है और उसके ऊपर लोडिंग हो रही है तो क्या डिफरेंसेस आ सकते हैं। So as per this particular standards, they are the two, as we discussed, the CHARPY and the ISO, but the most frequently the CHARPY is utilizing because of its frequent result and the best result which is get by this particular test. So the standard CHARPY B specimen is about 55 mm long, 10 mm square, and has a 2 mm deep, as this is the particular dimension is showing in here, and the V notch dimension is also mentioned here, which is faced by the particular material made by the machine. So the CHARPY specimen may be used with one of three different types of notches, that is the keyhole notch, U notch and V notch. So these are the opening of that particular site at that particular notch, which is defined by the V shape or the U shape or the keyhole shape. So the keyhole and the U notch are used for the testing of brittle materials such as cast iron and for the testing of plastic. So that particular shape of notches are utilizing for this. So the V notch specimen is the specimen of the choice for well testing and is one of the discussed here. So how this is to be striped, so that is the particular positioning is showing here in this particular set. So this Charpy test is providing a better result as compared to the IJO. As you can see, the impact of that particular striker is behind the particular notch. So that is how this particular test is to be identified. But in the IJO test, what is happening? The particular specimen is placed like this, and there is a notch here, and the striking of the hammer is in the front. The notch in the IJO is in the front of that particular hammer, but in the Charpy, the notch is the behind of the striking of the hammer. So that is how the test result of that particular material is to be varied. As you can see that in the Charpy test, the specimen is simply supported by the two yield, and in IJO there is a cantilever situation provided in that particular scenario. So to carry out the test, standard specimen is supported at its two end on an anvil and is struck on the opposite face to the notch by a pendulum. That pendulum is showing as a hammer. So the specimen is fractured and the pendulum swing through the height of the swing beam, a measure of the amount of energy absorbed in fracturing the specimen. तो होता क्या है बेसिकली, एक पोजीशन से इस पर्टिकुलर इनिशियल पोजीशन से हाइट को नाप लेते हैं, राइट? किसकी हाइट को नापते हैं? इस पर्टिकुलर यहां से इस हाइट को नाप लिया जाता है, दैट इज h। और जब ये स्ट्राइक करके हैमर कुछ ऊपर दूरी तक जाता है तो उस डिफरेंस को नाप लिया जाता है, एंड दैट इज द डिफरेंस which is identified by this Charpy test with this particular test, and that is how we can differentiate that how much that particular energy is absorbed by that particular material, and that is the point is mentioning over here. So conventionally, three specimens are tested at any one temperature and the result is average. If impact testing is carried out over a range of temperature, the result of energy absorbed versus temperature can be plotted to give the S curve, that is the curve that we talked about. So this shows that the fracture of these type of steels changes from the ductile to on the upper shelf to the brittle or the lower shelf as the temperature falls. So passing through the transition region, where the fracture, the passing through the particular transition region where the fracture will be mixed. So many specification talk, as you can see in the figure, that is showing the brittle and ductile nature of that particular material when the temperature is being changed before the examination or the test. So many specification talk of transition temperature, a temperature at which the fracture behavior changes from ductile to brittle. That is happened with that particular titanium, and that is how this particular changing of the temperature showing the various gross fall of the particular material reactions. As you can see in the figure, that particular observed energy in the joule, that is showing that particular the brittle nature is from the upper shell to down shell, and that particular ductile, that is the ductility is from that particular shell to there, and that is how the percentage of crystallinity and the temperature gradient is showing over there. So that is how. So what this curve is showing? So that is showing that the ductile fracture absorbs a great amount of energy than a brittle fracture in the same material. Knowing the temperature at which the fracture behavior changes is therefore of crucial importance when the service temperature of a structure is considered. Ideally, in the service structure should operate at upper self temperature, that is the upper self temperature, that is the ideal temperature, and the heat treatment condition, composition, whether or not the steel has been welded, welding heat input, welding consumable, and normal number of additional factors which are affecting that particular scenario of that particular material. So all the factors must be controlled if good notch toughness is required. So the austenitic stainless steel, nickel, and aluminum alloy do not show the change in the fracture behavior. The fracture remaining ductile even to a very low temperature. This is one reason why this type of alloy are used in the cryogenic applications. So there is some kind of a material which don't have any tendency to change themselves according to the change in the temperature. So as you can see, we are moving towards that how when the fracture is to be taking place. So it's a very simple thing that we discussed in the earlier slides, that the specimen which is made in the some specific dimension are placed on the anvil just in front of that particular hammer, and when we place that particular material on that particular anvil, a hammer is easily, that is how this thing is working. That particular thing is stopped here, and that particular hammer is freely moving. So after moving that, it is strike with the force, with the reaction, and that is how the particular energy is to be occur in the material. And when it does not reach that particular material, it will start breaking, and then breaking it just stop that the movement of that particular hammer to move more side, upper side. So that is how that particular height is showing that particular material is absorbed that particular energy. And that is how this particular test is to be taken. It is that simple as it is. There is no complication in that particular thing. And after the test, there is lots of analysis to be taken care, and there are the various scenarios taking place during the test also. That is how it is defined. So, in addition to the impact energy, there are two further features that can be measured. They may be found as a requirement in some specification. So these are percentage crystallinity and lateral expansion. The appear of a fracture surface gives information about the type of fracture that has occurred. So a brittle fracture is bright, a crystalline, a ductile fracture is dull and fibrous. As you can see in the figure, that is how हमें पता चल जाएगा कि किस तरह का मटेरियल वो बिहेव कर रहा है. वो डक्टाइल मटेरियल को बिहेव कर डक्टाइल मटेरियल के फ्रैक्चर को बिहेव कर रहा है या ब्रिटल फ्रैक्चर को बिहेव कर रहा है. सो आप फिगर में देख सकते हैं कि किस तरह से लेफ्ट साइड में डक्टाइल कप एंड कोन शेप बना है, और राइट साइड में आपके दैट इज द राइट साइड, दिस इज द वन showing the brittle fracture, and the brittle fracture is the bright and crystalline, a ductile fracture is dull and the fibrous. Sorry, this is the particular things, and that is how. So as this is showing in the particular brittle fracture is a bright and crystalline, a ductile fracture is the dull and the fibrous. As you can see in the figure, that is also showing here that in the highly ductile fracture in which the specimen need down to be a point like this, and that is the moderate ductile, and that is the brittle fracture without any plastic deformation, as it is showing here. So this is how the ductile fracture is also taking place in the cup and cone shape, which is identifying. So percentage crystallinity is therefore a measure of the amount of brittle fracture determined by making a judgment of the amount of the crystalline or brittle fracture on the surface of broken specimen. So later on, lateral expansion is measure of the ductility of the specimen. When a ductile metal is broken, the dust is deformed before breaking. A pair of hairs being squeezed out on the side of the compression face of the specimen, as you can see in this particular figure. So the amount by which the specimen deform is measured and expressed as a millimeter of the lateral expansion, that is defined by the ASME, American Society for Mechanical Engineering. B31.3, for example, require a lateral expansion. So this is the things which is showing here. So that is the thing which is to be providing the information that the material is, which kind of material is possessing the different things. So in this context, we are moving toward another kind of a test, that is called the broad weight test. And these drop weight test is also known as another kind of impact test, which is subjected a series of specimen and a progression of the temperature to a simple impact load from a guided free falling wave or a striker dropped in a vertical direction. So that is showing in the figure. It is another kind of a direct impact test which is showing the particular behavior. So the drop weight test determines the maximum temperature at which a beam specimen breaks or the temperature at which the fracture mode of steel changes from ductile to brittle, which is called the nil ductility transition, that is called the NDT. So the initial test is conducted at a temperature which is estimated to be near the NDT temperature. So the remaining specimens are then tested at a the progressive of temperature interval to determine the break and no break performance temperature within 10 Fahrenheit or 55 degrees centigrade. And that is how this particular test is to be performed, and this particular scenario is to be taken care. As you can see in the figure, there is a standard showing the ASTM E208 for the drop weight test for nil ductility temperature of ferrite steel. So what is the nil ductility? That is need to be identified. A drop weight determines the maximum temperature at which a beam specimen breaks or the temperature at which the fracture mode of the steel changes from ductile to brittle, which is called the nil ductility transition. And that transition is examined by that particular drop weight test, and that is how it is happening in that particular scenario of that particular temperature differences. And this is how this is all whole scenario of the impact test is to be taken care. And we will discuss more about this particular impact test in the later classes. That is how this impact test is performing on the various materials and how the particular things is to be happen. So the basic difference between the tensile between the impact testing, the Charpy and the I-jolt test is the difference between the I-jolt and the Charpy is the striking of the hammer. That in I-jolt the specimen is putting in the cantilever position, but in the Charpy test the specimen is projected or supported by the simply supported in the both side, and that is how the test result is very efficient in this particular Charpy test. So all the tests which is taken care by the ASTM standard and should be taking care of that particular temperature scenario in which this particular transition is taking place. So the upper self position of the material transition is the very much important. When the material temperature is down, that the lower by moving to the lower cell, so that the particular material will change their scenario, and the failure of the material will take place. So for the impact test, I just wanted to explain that things, and that is how all these things are related. So in the further test, we will be moving to the hardness testing. So what is the hardness, why it is required, we will discuss in the later class. So I am just telling you I am leaving this lecture with just a simple example of the hardness testing. So before that, we are just, as you can see in the figure, there is a two meshing gears, and that is why there is a hardness of this particular things is defining. So hardness is a characteristic of a material, not a fundamental physical property. So in the characteristic of a material, it is defined as the resistance to indentation. किसी के अंदर कोई इंडेंट हो रहा है या फिर कोई रबिंग हो रही है, तो उस इंडेंटेशन को किस तरह से वो मटेरियल रजिस्ट करेगा। आप देख सकते हैं इस फिगर में पर्टिकुलरली दो ही सेम मटेरियल से बने हुए एक दूसरे से मैश हो रहे हैं और एक दूसरे को छोड़ते हैं, तो उनके बीच कहीं ना कहीं इम्पैक्ट, कहीं ना कहीं फोर्सेस का लेन देन होता रहता है, जिससे कभी कभी वो एक दूसरे से घर्षण भी करते हैं, कभी कभी एक दूसरे के ऊपर इम्पैक्ट भी डालते हैं, इंडेंट भी डालते हैं। तो वो इंडेंट का क्या असर पड़ेगा मटेरियल को और कितना इंडेंट को मटेरियल सह पाएगा, ये सारी चीज़ों के बारे में जानकारी हम लोग हार्डनेस टेस्ट से लेंगे। So it is defined as the resistance to indentation, and it is determined by measuring the permanent depth of the indentation, कि कितना वो मटेरियल पेनिट्रेशन को, कोई मटेरियल अगर हार्ड है तो उसके अंदर कितना मटेरियल वो धंसा सकते हैं या वो पेनिट्रेट कर सकते हैं, जिससे कि उसकी हार्डनेस एग्जामिन हो सके। So when we using a fixed force load and a given indenter, the smaller the indentation, the harder the material. सो ये हमको वही चीज़ बताई गई है कि एक फिक्स फोर्स किसी मटेरियल के ऊपर हम अगर इंडेंट करते हैं, चुभाते हैं, तो जितना कम से कम इंडेंटेशन का एरिया बनेगा तो उतना ही उसका ज़्यादा हार्ड मटेरियल वो जाना जाएगा। तो ये सिंपल एक तरीका है इसको आइडेंटिफाई करने का कि आपके घर में एक आटे का गूंथा होता है, जब आटा गूंथ जाता है तो उसके अंदर अगर आप उंगली धसाएंगे तो वो धस जाता है। तो यही सेम मेटल के ऊपर भी परफॉर्म किया जाता है कि मेटल के ऊपर अगर आप किसी दूसरे मेटल से इंडेंट करते हैं तो वो कितना उसको धसने देता है या फिर उसको रजिस्ट करता है, और यहीं से हार्डनेस का एक जो इंडेंटेशन प्रॉपर्टी है वो बाहर निकल के आती है। So indentation hardness value is obtained by measuring the depth of the area of the indentation using one of the over 12 different test methods. There are the various kind of a hardness test according to the thickness of the material, according to the requirement of the material. कोई मटेरियल की थिकनेस ज़्यादा है, कोई पतले थिन शीट में है, तो सबके ऊपर एक सेम लोड अप्लाई नहीं कर सकते। तो उस चीज़ को ओवरकम करने के लिए अलग अलग तरह के हार्डनेस टेस्ट को डिफाइन किया गया है। सो वी विल डिस्कस ऑल इन द लेटर ऑन द क्लासेज। So this is why this particular hardness test is required. So we are moving towards how the hardness tests work. We will discuss this thing in the later class with the details. A hardness test is typically performed by pressing a specifically dimension and loaded object indenter, as we discussed. The indenter, it is either in the diamond cone shape, either in the ball indenter, that depend upon the thickness of the material, and that is how we defining these things. So the hardness is determined by measuring the depth, as we discussed earlier in the slide, that the indentation, penetration, or measuring the size of the impression left by the indentator, that defining the hardness of that particular metal. So the hardness test that measure the depth of indenter penetration include the Rockwell instrumented indentation testing and the ball indenter hardness test, that is the Brinell hardness test. So as well as there are another kind of hardness test also, the hardness that measure the size of the impression led by the indenter, that is including the Baker loop and Brinell. So that is how these particular tests are categorized, and that is we will discuss in the later class in the detail that how this particular individual Rockwell test is taking place in the material, and that is identify the particular hardness of the material and to examine the particular hardness of the material. So hardness that is not only single identified by the indentation, it is also can be defined by the scratching of the material also. That is how much that particular material surface is resists that particular scratches, and that is how this particular hardness is to be defined. So we will discuss this all in the detail in the later lecture, in the next lectures. So till now I am holding this, and thank you.